Right, so we will move on to the next one. So this is again a straightforward question. So you have given an elementary reaction. First thing that you need to identify that elementary reaction. The order is stoichiometric. So write down the rate law. So what is happening here? Wait. Right, so write down the rate law. So you need to write down the rate law here. And since this is an elementary reaction, so you can automatically write. So I have used a different font now. So write down the rate law. So this is an elementary reaction. So automatically you can write. So rate is equal to the rate constant, that is K times concentration of a gas. And the order is 1. So you don't need to put 1 as well. So the order is 1. R is equal to Ka gas concentration. Then the above reaction was started by introducing 1 mole of A. So we have 1 mole of A initially. So that is good. At 300 Kelvin. And the initial pressure of 30 kilopascal increased to 32 kilopascal in 10 seconds. So remember, it was after 10 seconds. Then the experiment was repeated at 400 Kelvin using the same amount of A. And the initial pressure is 40 kilopascal. Now it was changed from 30 to 40 because temperature is different from 300 to 400. And now the pressure is increased up to 45 kilopascal. The rate constant of this reaction 300 and 400 is K1 and K2. They have given respectively the rate constant. And the first 3 questions you can see calculate the amount of A decomposed in 10 seconds or at 300 Kelvin, and calculate the amount of A in after 400 Kelvin, and giving reason show that K2 is greater than K1. So I will stop the screen and we will do the calculation. Sorry. So okay, so you have the reaction. So A gas, we have B gas and C gas. So we have 1 mole here. So we have 2 situations. One is at 300 Kelvin, the other one is at 400 Kelvin. So we have 1 mole here. And the pressure that is increasing is from 30 to 32. And here this was 40 to 45. Right? So don't forget, initially we have only A. Okay, initially we have only A. So in primarily this 30 kilopascal is given only by A at initial condition, right? So if you think the amount of A that is dissociated here is X, you know there should be X forming here and X forming here. So the total moles at equilibrium is 1 minus 6 plus 6 plus 6. So you can cut, it is 1 plus 6. In the same way, you can plug here minus y, y, y. So the total moles at equilibrium is equal to 1 plus y. Okay. And then you can apply PV is equal to nRT at the initial condition, at the final condition for these 2 cases, and you can find X as well as Y. Okay. For an example, for the initial condition, if you add PV is equal to nRT, pressure for the initial condition is 30. Volume let's take as B. N is 1 mole of A. Let's take R as same. Temperature is 300 Kelvin. So we have this first equation. Okay. 30 times V, 1 mole, R 300. At equilibrium, the total pressure is 32. volume is still V, it does not change. Now N is 1 plus X, total number of moles, R is same, and the temperature is 300 Kelvin. Okay. So this is equation number 2 and equation number 1 and 2. So the only thing that you does not know here is V and X. But when you divide 1 by 2, automatically V is cancelling out. So there will be this equation 30 over 32 will be equal to R and R will be cancelled. 300 will be cancelled. So it will be 1 over 1 plus X. Okay. And when you do the same thing here it will be 40 over 45. That is going to give 1 over 1 plus 5. So using these two, you can find the dissociated amount at 300 Kelvin as well as 400 Kelvin. Okay. Okay. Did you understand? So I have a question. So can we consider this as an equilibrium reaction? Or which reaction? This particular one or the previous one where the liquefaction happens? This is not an equilibrium reaction, in fact, because you can see only one-sided arrow is given here, right? But you can imagine this as an equilibrium reaction within the first 10 seconds. Because this reaction, when you allow it to happen continuously, all A will be consuming and B and C will be forming at the end of the reaction. There will be no A, there will be only B and C. Because this is one-sided, not reversible. This is an irreversible reaction that is happening continuously, and B and C will be forming, and there will be no A at the end. So A and C is only there at the end of the reaction. But here they have given the change in pressure after 10 seconds, indicating that A should be remain within this 10 seconds. It is confirmed by how much dissociated. They are asking how much dissociated. It is confirmed by the question. Okay. But this is not an equilibrium reaction. This is an irreversible reaction. You need to consider at only first 10 seconds. Okay. So did you understand? So here there will be 30 plus 30x is equal to 32. So 30x is equal to 2, x is equal to 2 over 30. Then here y is equal to 40, 40, 40, 45. So y is equal to 5 over 40. Okay. This is 1 over 15 and this is 1 over 8. Okay, so you have understood, right? So this is the amount that is dissociated. This is 1 over 15 at 300 Kelvin. And here at 400 Kelvin, the dissociated amount is 1 over 8. Okay. So you can understand what is the larger value. Here 1 over 8 is greater than 1 over 15, which should gives you the idea at higher temperature, higher amount of A is dissociated, which means rate at this temperature is faster than this one at 300 Kelvin. So this is essential to answer the next question, because in the next question they are giving reasons, show that K2 is greater than K1. You can use a calculation method like using the rate equation, R is equal to K1 times concentration of A. Right, you have found X here, so 1 minus 1 over 15, and you can just write down the volume that is negligible over the volume V. And you can show in the second equation as K2, R is equal to K2 times concentration of A, 1 minus Y over V. So you can do all these things. You can show this by using a calculation where K2 is greater than K1. But you don't need to do that, because you just need to understand and explain using your words. What is you have to explain here? The dissociated amount at 300 Kelvin is lower than the dissociated amount at 400 Kelvin. So since the dissociated amount here is greater, the rate here is faster or greater or higher. Therefore, K2 should be greater than K1, because we are considering same time, 10 seconds. That is very important to mention. Okay. So try to understand this concept. Right. So this is again a nice question where you need to understand irreversibility and reversibility nature, as she asked in the question. So it is very necessary to understand within 10 seconds this entire reaction does not happen, and only few amount of A is dissociated. And in fact, this is not reversible. This is an irreversible condition where you have A going to B and C. Okay. So when you having a reversible reaction, always remember when A goes to B and C, there is another reaction that is happening in the backward. B and C combine and form A as well. For an example, if you want to think about this more productively, think about, let's say, a bus. We have a bus like this, okay, and the maximum population that we can have here is 54. Okay, so few people initially starts to get in, and few people initially going out and coming back and again start getting in. So initially there will be no people here in the bus. So there will be 1, 2, 3 people that is getting in. So this is like the forward reaction. Okay. So initially this forward, if this is reversible, initially this forward reaction happens very fast, because since the bus is empty, there will be more space and getting in. And finally, after a certain time, there will be people that is coming out. So when one come out, one goes out, two goes out, three goes out, like that. So it goes out. So this is like the backward reaction. Okay. But there will be a point where the number of pupils within the bus does not change. Like, let's say we have 20 people in the bus, and there will be one that is coming in and there will be one that coming out, which gives the idea the number of people within the bus does not change, and the forward reaction rate and the backward reaction rate is equal, and the number of people does not change mean the concentration of the people here is does not change, just to understand. So this is the condition of equilibrium, right? But here this is just a forward reaction. We are getting in, and at the end of the day, until all people finish here, it will get. But don't forget, no reaction is 100% perfect. Okay, this is very important thing to understand as well. Okay, so this is another straightforward question. So you have given enthalpy and entropy data for the dissociation of weak acid, HA, given below. So you have given the data of HA in the aqueous phase. Dissociation of HA in the aqueous phase gives you A minus aqueous and H plus aqueous, and its enthalpy and entropy is given. Okay. And they have given the gas phase change to the liquid phase. So dissolution is given of A minus, H plus, as well as H as well. So write down the balanced chemical equation for the dissociation of HA in gas phase. So this is straightforward. You can write down HA in gas phase. Okay. So you can write down the dissociation. H plus in gas phase, right? Plus A minus still in the gas phase, because all these are in gas phase reactions. Okay, so this is straightforward and easy. Calculate the following for the dissociation of HA in gas phase. So you need to find dissociation of HA in gas phase. So here you need to find enthalpy, and you need to find entropy, and you need to find Gibbs free energy for this particular equation. Okay. So let's stop sharing and let's see how to calculate this. Right, so we have the gas phase reaction. So HA gas will be giving H plus gas and A minus gas. Okay. So here we need to find enthalpy, entropy, and Gibbs free energy. But the advantage here is they have given some additional information. See, they have given how HA gas can be converted to HA liquid. In fact, HA aqueous. Okay. So the enthalpy is given minus 150. Okay. So this is delta H. And entropy is given minus 100. I think the units are different. See, be careful with the units, because enthalpy is given in kilojoule per mole. This is given in joule per mole. Joule per mole per Kelvin. Okay. So this is one that they have given. They have given another one. How to convert this and how to convert this. So H plus aqueous dissolution, A minus aqueous. And finally, you can see HA, H plus aqueous, A minus aqueous. This one also they have given. The first equation. So here the enthalpy is given as 1 and S is given as 95. And here the enthalpy is given as A gas to H plus gas to H plus AQ is minus 1100. This is delta H. Delta S is given as minus 1200. And for A minus, this is minus 200 for delta H and minus S for minus 2000. Okay, so all these values are given here. Now I have a very simple question. Okay. Right. Why do you think they have not given like delta H theta or delta S theta here? Can you answer this question? So I will share the screen again just to show. So here they have given delta H and they have given delta S here. And they have not given these values as delta S theta or either delta H theta. Why is it? Can you answer this question very quickly? Why do you think? So I will give you a clue. Think about the temperature that they have given. What do you think? Yeah, the straightforward answer is that they are not mentioned in the standard condition. So you know what is the standard temperature for enthalpy calculation? We take it as 298 Kelvin, right? So here they have considered this as 300 Kelvin, right? So it is necessary to understand. That is why they have given this as delta H, because these are not standard values. It is very difficult to get these values in the standard condition. That is the problem. Okay. Okay, so the enthalpy, entropy, and Gibbs energy change. So you can understand here. In this thermochemical cycle, okay. So I will again stop sharing. Right. So now in this thermochemical cycle, to find the enthalpy change for this gas phase dissociation, you can use the Hess's law. Why? Because you know this enthalpy, this enthalpy, as well as this enthalpy in this thermochemical cycle. So the only thing that you does not know for this entire thermochemical cycle is only this. So in primary, if you take this as delta H for the HA gas dissociation, okay, so this one plus this two should be equal to plus, where is it? Plus minus 1100 minus 200 should be equal to minus 150, and this HA aqueous that they have given, the value is 1 and 95 for the entropy. So this is delta H is 1 and entropy is 95. So this should be minus 1. Okay. The only thing that you don't know here, this is plus 1, is this one. This becomes straightforward because when you have this thermochemical cycle, so don't ask me how did you draw this thermochemical cycle. I did not draw the thermochemical cycle. I just wrote the gas phase dissociation, and based on the information that they have given, I tried to make HA aqueous from HA gas. So I just put this, and this. And when you write down these three, it gives me the idea, okay, now this equation becomes HA dissociation in the aqueous phase, which is this and this. So using the enthalpy values of this each step, using the Hess's law, you can find enthalpy. And in the same way, using the entropy values here, they have given the entropy values. The entropy values here. You can find this entropy change for the gas phase dissociation. Then you know the gas phase dissociation for the enthalpy, and you know the gas phase dissociation, the entropy. Then you need to find Gibbs free energy. Okay, and then if you want to find Gibbs free energy, delta G is equal to delta H minus T delta S. This is the equation. Okay, but remember, if you put delta H theta is equal to T delta S theta, this is wrong. Okay, I have told you before, this is wrong because they are asking at 300 Kelvin, not the standard temperature. Okay, so here when you want to plug this equation, you have to put delta G is equal to delta H minus T delta S. So delta H you have found using this chemical cycle. Temperature is given as 300 Kelvin, and entropy also you can find using this one, and you need to only find delta G. But remember, when you are plugging here, make sure you do the unit conversion clearly, because enthalpy that you are going to calculate here will be in kilojoule per mole. Okay, and entropy will be joule per mole per Kelvin. So you cannot put here as it is. Either you need to convert joule into kilojoule, or either this kilojoule into joule. It's better you convert this joule into kilojoule. Okay, and then you substitute and find the value for delta G. It is important to understand. And I will tell what is delta G that they have obtained here. In fact, when you find delta G here, you will see it will be 192.5 kilojoule per mole. Okay. Okay. So you understand how to build this one, right? You write down the basic steps, then you combine to get a thermochemical cycle, and then you plug the Hess's law, because enthalpy, entropy, Gibbs free energy all are state functions. And then you find enthalpy and entropy. Then you plug this in the Gibbs free energy equation, and then you find delta G. And here, when you find this delta J, it is 192.5 kilojoule per mole. Okay. So this is important to answer our next question, because next question they ask is, comment on the spontaneity of the dissociation of HA in the gas phase at 300 Kelvin. So you can write, since delta G is positive, this reaction is not spontaneous, or this reaction is non-spontaneous at this temperature, since Gibbs free energy is positive. Okay, because to make one reaction spontaneous, your delta G should be negative. Okay. Calculate the Gibbs energy change for the dissociation HA in the aqueous phase at 300 Kelvin. Okay. So there is no problem here to find in the aqueous phase, because for the aqueous phase, they have already given all the information. See here, enthalpy is also given, entropy is also given. So just you need to plug the Gibbs free energy equation. This equation here, delta G is equal to delta H minus T delta S. Then you can find the Gibbs free energy. Okay. And when you find the Gibbs free energy, you will see this aqueous phase will be minus 27.5 kilojoule per mole. So which you can easily identify, a weak acid like HA will not undergo dissociation in the gas phase because it is 192 positive. But here in the aqueous phase, it is minus 27. So that is why gases like acetic acid, formic acid, even HF, those are weak acids. When in water, they get dissociated, because you can see the dissociation is spontaneous at aqueous phase. Okay. So this is nice, because the first one, they gave information to find the dissociation Gibbs free energy in the gas phase. And in the second one, they are asking you to find this in the aqueous phase. And when you find this, you can see in the aqueous phase, the Gibbs free energy is minus 27.5 kilojoule per mole. This is spontaneous in the aqueous phase, but not in the gas phase. Then, at what temperatures does the Gibbs free energy change of the dissociation of HA in the gas phase become equal to its Gibbs free energy change dissociation at the aqueous phase? So now this becomes straightforward, because, so I will erase entire thing now. Okay. So what you have here is HA gas is going to give H plus gas, A minus gas. And the other one is HA liquid or HA aqueous, H plus aqueous, A minus aqueous. Okay. And here for delta H, you know, delta S, you know, and delta G you found, that is 192 something. And here also they have given delta H, delta S, and delta G is minus 27 something kilojoule per mole. kilojoule per mole. Okay. Now, what they are asking is, what will be the temperature of the gas phase equilibrium? For an example, let's say this is equilibrium. In the gas phase equilibrium, what will be the temperature T at which the Gibbs free energy will be equal to the Gibbs free energy in the aqueous phase, which is this value. Okay, so it gives you the idea when you have this conversion and your equation is delta G is equal to delta H minus T delta S. They are asking about this temperature. What is this temperature? If I want to get the same Gibbs free energy as the liquid phase. Okay. So what are the values? Delta H and delta S. What do you think? The values of delta H and delta S. For that they have given, see the assumption. I will show the assumption. See, assume that delta H and delta S are independent of the temperature. That means, although you are trying to calculate a different temperature, in practice, when you change the temperature, these delta H and delta S values that you have calculated here at 300 Kelvin will be changed automatically. But you need to calculate the temperature here using delta H and delta S, which it should give you, or it should take you the idea that when the temperature is changed, delta H and delta S can be even changed. But you have to make an assumption here, it does not depend upon the temperature. Okay, and then you know these values now already you have calculated for the gas phase equilibrium. You have to just plug in here using these values and you have to just find the temperature. That is the only thing that you don't know here. Okay, so this makes this question summarized. Right, so did you understand this very quickly? Okay, so here we started with the gas phase equilibrium, this one, the equation. And okay, chat, what is that? Okay, that's good. And then we have to find enthalpy, entropy, and Gibbs free energy. We use this data. And we need to find the spontaneity. So we saw that in the gas phase reaction, this is not spontaneous, but in the liquid phase, it is spontaneous. And then at what temperature you need to consider this liquid phase Gibbs free energy minus 27 something in order to think what temperature. So in the idea is when you have a temperature that we can calculate like around 370 Kelvin, which should give you the idea normal room temperature. So you can make it as liquefied, so which gives you dissociation. Okay. The only thing that you need to understand here, this is a nice question even to think about the chemistry also. Okay, because you can understand the gas phase dissociation is spontaneous, non-spontaneous, so it does not happen. But in the liquid space, when you go for like the liquid phase dissociation, it happens. So that is why, for an example, a gases like acetic acid in aqueous phase, for 1M, it gives a pH around 3 because the dissociation is spontaneous. So it will give some amount of H plus in the aqueous medium. Okay.